Let's conduct a thought experiment. Imagine two identical twins standing on Earth. One twin decides to stay behind, while the other boards a spacecraft and launches toward a star 8 light-years away, traveling at 80% the speed of light. The math reveals a strange paradox. The twin on Earth ages 20 years, while the traveler ages 12. But since motion is relative, the traveler could claim they sat still while Earth moved away. In that valid perspective, the Earth twin should be younger. Both of these perspectives are mathematically sound, but they cannot both be true when the twins reunite. You can't have two people who are each strictly younger than the other. Resolving this contradiction means giving up a deeply held human assumption, the idea that a second is a rigid, universal unit of measurement that ticks at the exact same rate for everyone. In 1905, Albert Einstein was wrestling with two incompatible sets of rules governing the universe. On one hand, he had the laws of motion defined by Isaac Newton, and on the other, the laws of electromagnetism discovered by James Clerk Maxwell. This diagram demonstrates Newton's classical rules of relative velocity. If a girl on a sled moving at 1 meter per second throws a snowball forward at 1.5 meters per second, an observer on the sidewalk adds those speeds together. To the bystander, the snowball is traveling at 2.5 meters per second. Speed is entirely dependent on the observer's frame of reference. But looking at this illustration of a moving car, Maxwell's rules dictate that light behaves completely differently. Even if the car is speeding forward, the light emerging from its headlights reaches the pedestrian on the sidewalk at the exact same constant speed, roughly 300 million meters per second. The speed of the car does not add to the speed of the light. You calculate speed by dividing distance by time. If the speed of light refuses to change regardless of the observer's motion, Einstein realized that the variables underneath it, distance and time, had to bend and warp to keep that speed constant. To see how this physically works, imagine the simplest possible timekeeping device inside a moving spacecraft, a photon clock, where a single particle of light bounces between two mirrors. Every bounce counts as 1 second. Notice in panel B of this diagram that as the spacecraft flies forward, an outside observer on Earth doesn't see the light bouncing straight up and down. Because the ship is moving forward, the light has to trace a much longer diagonal path to hit the top mirror. Comparing this back to the stationary clock, the contradiction is obvious. The light in the moving ship is traveling a further distance. That because the speed of light cannot speed up to compensate for that extra distance, the duration of the tick itself has to take longer to complete. This shift forces a change in space. From the traveler's perspective, their clock feels perfectly normal. For them to reach a destination 8 light-years away in just 12 years, the universe must compensate. To the traveler, the distance itself physically shortens in the direction of travel. This stretching and squeezing even affects an object's mass. Usually, adding energy to a ship makes it go faster, but as you approach light speed, the universe prevents you from crossing that barrier. Instead of moving faster, that extra energy is converted into pure mass, making the ship heavier and harder to accelerate. All of these physical adjustments serve one purpose: protecting the absolute speed of light. The faster an object moves through space, the slower it moves through time. By simply traveling fast enough, velocity becomes a functional biological time machine. So, returning to our two twins, if motion is perfectly relative, how do we know the twin in the spaceship is the one who comes back younger? This graphic traces the reality of the traveler's journey. Time dilation is perfectly symmetrical only as long as both twins remain in what physics calls an inertial reference frame, meaning they are traveling at a constant, unchanging velocity. But the traveling twin doesn't maintain a constant velocity. To return to Earth, they have to fire their engines, heavily decelerate, turn the ship around, and accelerate back in the opposite direction. That massive acceleration violently breaks the symmetry between the two perspectives. The twin on Earth simply experiences a continuous, unbroken timeline. The twin in the spaceship physically jumps between different reference frames. Because the traveler is the only one who underwent acceleration to reverse their trajectory, their timeline is the one that shifts. When they reunite, the traveling twin is unmistakably younger. Special relativity proved that space and time aren't separate stages for events to happen on. Einstein realized they are woven together into a single, malleable continuum, a four-dimensional fabric called spacetime. Einstein realized that being pulled by gravity is physically indistinguishable from being accelerated by a rocket. Because massive objects warp the fabric of spacetime, they force everything nearby to accelerate toward their center. Since acceleration stretches time, these gravity wells act as permanent time dilation zones. At the cosmic scale, the gravity near a supermassive black hole curves spacetime so severely that an hour spent on a planet in its orbit equals 7 years passing back on Earth. But this rule plays out right here on the human scale, too. Earth's mass creates a curve in spacetime, and that gravitational pull is slightly stronger at the surface of the planet than it is higher up in the atmosphere. Because gravity causes constant acceleration toward the Earth's center, time ticks slightly slower at ground level. From a strictly biological perspective, your head is older than your feet.